Hi everyone. So I guess we can start now. So today's lecture will mainly be about some trees and some popular tree algorithms that you see in competition a lot. So basically, like a quick overview of what we're gonna do. So we'll quickly go over some tree fundamentals and then like some tree systems like BFS and DFS, and then we'll move on to two pretty popular algorithms that you'll see a lot in programming competitions, which are binary listing and the lowest common ancestor. So just like to start off, like what exactly is a tree? A tree is basically like it's basically a graph, and like a graph is like a set of relations between nodes. So here you can see that like we have nodes in the circles like 1, 2, 3, 4, 5, like etc. are all nodes, and then they're all connected by edges, which denotes a like relationship between nodes. Like you can see that 1, 2 is an edge, 5 and 8 are connected by an edge. And a tree is just a specific case of a graph that satisfies some special properties. So the first property is that a tree is an acyclic connected graph, and the first property will look at its connectedness. So first of all, the tree must be connected. Like for example, here you can see that on the left one, this tree is not connected because like node 1 cannot reach node 8, for example. So like this is not a tree. Here node 1 cannot reach node 5, for example, and this is not a tree. And on the right side, you can see that every node can reach every node. Like node 1, there's a path from node 1 to node 10. We have some edges. So this one satisfies the condition. The other part of acyclic connected graph is acyclic. So a tree cannot have cycles in it. And like what I mean by cycle is like kind of a sequence of paths that will like lead you back to your second node. Like for example, here 1, 2, 3, 1. There's like you can see there's a sequence of edges that you can like start from one and end at one, without going to the same edge twice. And this is bad, so this is not acyclic. But if you look at these two, you can see that there are no cycles and it's connected, so therefore these two are trees. So like some examples of trees, you can see that all of these examples are acyclic and connected. There's also another property of trees is that a tree will always have n-1 edges. So like, for example, if I start off with these 5 nodes and I just add an edge every time, such that the graph becomes connected and acyclic, you can see that we will end up with a tree. So just like remember these 3 properties like acyclic, connected, and n-1 edges. And you can see that any of these 2 implies the third. So if you have a graph that is connected with n-1 edges, this implies that it's acyclic, and if you have an acyclic graph that's also connected, it implies that there's n-1 edges, and like this is like a nice property that you can use. So some quick tree terminology. The degree of a node is the number of edges going out from it. So for example, here node 1 has a degree 2 because it's connected to nodes 2 and 3. A leaf node is a node on a tree with degree 1. So here 3, 4, 5 are all leaf nodes, and the distance between 2 nodes is the number of edges on the shortest path. Like for example, the distance between 1 and 4 is 2 because you go from 1 to 2 to 4, and this goes through 2 edges. And you can also notice that there's only one path between any 2 nodes. And like the distance between 4 and 3 is 3 because you go from 4 to 2 to 1 to 3. Next we'll define like the idea of a root. So the root is like not really an intrinsic property of the tree, but like rather like we choose some node and we let this node be the root. Like for example here, we've chosen node 1 to be the root, here we've chosen node 2 to be the root, and here we've chosen node 6 to be the root. And even though these are all like the same tree structure, they have different roots. And just like remember that root is something that like we decide, and it's like not some property of the tree. And like a lot of other properties will be based like off of the root. Like for example, the depth is defined as the distance of a node to the root. So for example, in this node, our root in this tree, our root is 1, and the depth of nodes 2 and 3 are 1 because they have a distance of 1 to the root, and the depth of nodes 4, 5, 6, and 7 are 2 because they have distance 2 to the root. Like you can go from 4 to 2 to 1, and then 5 to 2 to 1, and then 6 to 3 to 1, and etc. And here's just like some more examples of like depths in different trees. Like I guess like you can like verify for yourself that these are correct. Okay, now we'll introduce the idea of the parent. And a parent is basically the the node that's adjacent to a node that's like closest to the root. So for example, here in this tree, we've kind of drawn out directed edges to all the parents. Like the parent of 2 is 1 because like 1 is the closest node on the path from 2 to the root. Here the parent of 4 is 2 because 2 is the closest node on the path from 4 to 1. And yeah. So like now we can like go get to the idea of ancestors, and the ancestors of a node are basically just every node on the path from that node to the root. So like the ancestors of 6 are 6, 3, 2, 1 because the path from 6 to the root 1 is 6, 3, 2, 1. And like here, the ancestors of 11 are like defined similarly. Like the ancestors of 11 are 11, 4, 7, 2, 1. So next, like we have subsequent descendants, and this is kind of like the opposite of ancestors. So I guess like formally it's defined as like the set of nodes that are that have the subtree of a node x is the set of nodes that have x as an ancestor. So like for example, the subtree of 6 is 6, 12, 13, 8, and 5, because these all have 6 going on the path from them to the root. And like you can see here, the subtree of 11 is 11. So now like let's get into like some common ways to represent a tree. So like one of these is adjacency lists, and you'll see this one probably the most often. Basically for each node, you just store a list of all the outgoing adjacent nodes. So like for example here, you have that node 1 is connected to nodes 2 and 3. So in the adjacency list for node 1, I store 2 and 3. And like the same thing with 2. 2 is connected to nodes 1, 4, and 5. So in the adjacency list of node 2, I'll store the nodes 1, 4, and 5. And like this continues for everything.
Yeah. Just a quick note as well, we've posted these slides on the website already, so you can follow through if you'd like that. So next we'll talk about how to compute some of these properties. So for instance, we want to compute for each node what the parent is, what the depth is, and what the subtree size is. So just to recap, like the parent is the node closer to the root, the depth is like how far it is from the root, and the subtree size is how many parents are kind of like including it and below it. So we can solve this using something called DFS, and I'll quickly kind of go over how to implement this. So in our input, we'll store our tree. So this is kind of how you'll see trees represented in a lot of problems. So you'll be given the number of like nodes in your tree, the number of circles, and then you'll be given n-1 edges that represent kind of like 2 nodes at the end of the edge. So this means like 1 is connected to 2, 1 is connected to 3, 2 is connected to 4, and 2 is connected to 5. So what we'll do is we'll first kind of create our adjacency list from this representation. So we'll create our input template. We'll read an n, which is the number of nodes we have. Then we'll create our adjacency list. So our adjacency list will we'll have like an empty list at the beginning for every single node. And for now, we're going to one index our nodes to make them match up with what we have on the slides. So to now populate our adjacency list with our edges, we'll go through each of the edges in our input. So like 1, 2, 1, 3, 2, 4, and 2, 5. U and V will be the 2 nodes the edge connects. So, and then U is adjacent to V, so you want to add V to U's adjacency list. Similarly, we also want to add like the reverse way because U is also adjacent to V. So we'll kind of like add both kind of connections. So now let's print out our adjacency list just to make sure it looks right. So I'll start. So this is what our adjacency list looks like right now. So if we look back at our we look back at this slide, so we can notice 1 should be adjacent to 2 and 3, which it is. 2 is adjacent to 1, 4, 5, which is the same, and the rest are also identical. So we've correctly built our adjacency list, and now we can begin computing the properties. So the properties we want to compute are parent, depth, and subtree size. So we'll initialize all of these to just be kind of like none. So first I'll make a parent array be all none. Then depth, I'll also initialize, depth I'll initialize everything to be 0. And then size, I'll also initialize everything to be 0. Okay. Okay, whatever. So then now I'll write my DFS function. So I'll store what node I'm currently at, and I'll also store the parent of my current node. So let's first kind of code the skeleton of our DFS, where we'll kind of traverse through every node in our tree. So we can use our adjacency list for that. So for every neighbor, in adjacency list of node, so this is just going through everything that's adjacent to the node, we want to try and call DFS on that. But notice that the parent of our current node is also adjacent to it, so we don't want to go back, we only want to go down to its children. So we'll first check if neighbor is parent, then we'll skip this one and continue for our children instead. Then we'll call DFS on this child. So we'll call DFS on neighbor, and now the parent of our neighbor, after we go down, will be our current node. So like our child, we're going down to our child, the parent of our child is the current node. So we'll call DFS like this. Now that we have kind of the skeleton, we can begin to calculate our the values that we want. So since DFS is called with a node and that node's parent, we can simply assign the parent of the node to be the parent. Then to update the depth, for all the children, the depth of a child is 1 plus its depth. So depth of neighbor equals 1 plus depth node. Or actually, I think it would be more suitable to call this child, since that's kind of what we're making it here. So the depth of a child is 1 plus the depth of the current node. Okay. And finally, for the size, we'll initialize the size of every node to be 1, since that's kind of like the size of a subtree of a node by itself is just 1. And then we'll start looking at its children and adding kind of the size of that subtree to it as well. So size of node will add the size of the child. And basically what this does is it takes its node and it goes through every child and adds the number of nodes in that subtree to its entire count, giving us the total count of our node's subtree. So we can run this DFS by just running it starting from our root node, which we'll call 1 with parent none. So after this runs, it should populate all of our arrays, and we can just check that they're right by doing, for example, we'll print out the parent array, we'll print out the depth array, and we'll print out the size array. So after running this, so we see, first of all, this is a parent array. So our root, which is the first node, has no parent since it's the root, that's right. Then the second two nodes, 2 and 3, have parent 1, which is right. And finally, 4 and 5 have parent 2, which is also what we have here. Then, looking at our depths, we should have node 1 has depth 0, 2 and 3 have depth 1, 4 and 5 have depth 2. We also have that there. And finally, you can also check that the subtree sizes match up. So one consideration when using DFS to solve actual problems is that they'll generally give you very large inputs. And how our DFS works is by recursion. So like the function recursively calls itself. But Python has a quirk where it will by default limit your recursion size to 1,000. So after it calls itself 1,000 times, it will error out. But since our inputs are usually maybe on the order of 100,000, we don't want it to error out after 1000. So we can increase this bound by using this line right here. So sys.set recursion limit to something really big like 1 million. So usually you'll see a lot of people have maybe this at the top of their code if they're doing DFS. So right now this won't affect anything since our tree is only 5 nodes, but once we run into bigger inputs, this will be useful. So if we run code, it's still the same thing. Now we'll step through we'll kind of simulate DFS like one step at a time. We start with the root and we initialize, this should be depth 1 is 0. But we initialize everything so that the depth is 0 and the subtree size is 1. Then we iterate down to its child. So here we set its parent to the node we were previously at, and we add 1 to its parent's depth to find its depth. So we set the depth to 1, and we also initialize the size as 1. Then we go to its child. Its parent is node 2, its depth is 1 more as well, and its size is 1 since it's a leaf node. Then, when we go back to node 2, we want to increase its subtree size by however big the subtree size of this is, since this node is included in the subtree. So we'll add 1 to there. Then, similarly, we'll go to this node and increment our subtree size again. Then, when we go back to node 1, we want to update the subtree size of node 1 so that it reflects all of these nodes that are in here. So we'll add the subtree size of node 2 to node 1, bringing it to like the 4 nodes that we visited so far. Then we'll go to our final node, which is node 3, which is a leaf node, and then we'll update our size again to have a size of 5. So this is kind of a step-by-step run through of how this DFS works. Are there any questions either about either any of the updates or the code itself? Okay, so next we'll be covering a technique called binary lifting.
Okay, so the motivation for binary lifting is basically let's say you have n nodes and q queries, and each of the query consists of a node v and an integer k. And for each query, you want to find the kth parent of node v. And if you don't remember, the kth parent is basically you follow the parent k times. So for example, the 4th parent of 5 is 1 because you go from 5 to 4 to 3 to 2 to 1. And the parent of 7 is 6 because you just go from 7 to 6. For the sake of this problem, we're kind of going to represent the parent as a function. So basically, par of u will just return the parent of u, and for some notation, we'll say par squared of u is the parent of u, and par cubed of u is the parent of the parent of the parent of u. So you can basically just compose the parent function on top of a node to get its kth parent. However, if we just did this, it would be O of k per query, and we can see that k is less than or equal to n, which is less than or equal to 2e5. And there's also 2e5 queries. So if we just compose the parent function on node v k times, we get n times q times complexity, which is kind of slow. So how can we do this faster? One thing you'll notice about our parent function is that we can compute the 2 to the ith parent pretty easily. For example here, we're initially given all the parents of u. If we wanted to compute the second parent of u, we just have to compose the parent function upon itself. For example, the parent of 7 is 6, let's say. And so the second parent of 7 is going to be the parent of 7, which is 5. And now we can go to the 4th parent of u as well. So the 4th parent is just composing the second parent 2 times in a row. You can see the 4th parent of 7 is the second parent of the second parent of 7, which is the second parent of 7, which is 5. And the second parent of that is 3. And we can keep going for all the powers of 2. The 8th parent of u is the 4th parent of the 4th parent. And notice that at each step, for example, 8, to find the 8th parent, we only needed to know the 4th parents of all of those. And to find the 4th parent, we only needed to know all the second parents. So that means we can compute the 2 to the ith parent for all of u in O of n if we're given the 2 to the I minus 1 parents. And since there are only like log base 2 of n, like i's that we should check, we can compute the 2 to the ith parent of u for all of u in O of n log n. And this is like O of n per layer. And like each layer is just like computing the 2 to the ith parents given the 2 to the I minus 1 parents. So now we have this like useful thing, which is like we can now like find the 2 to the ith parent of u, which is kind of useful because now instead of like jumping up one at a time, we can jump up by like a power of 2. And powers of 2 grow pretty fast, right? So now we'll show how we can get the kth parent of a node by only using parents that are a power of 2. So looking at k, we know that any integer can be decomposed into like a binary representation, which is basically a sum of powers of 2. Like for example here, 3 can be decomposed into 2 plus 1, and the 5 can be decomposed into 4 plus 1, and 11 is 8 plus 2 plus 1. And we can see that we can, therefore we can find any kth parent by only using our parents of 2 to the i's. So like for example, the third parent of u will be the same as finding the first parent of u and then finding the second parent of that. And then the fifth parent of u is the same as finding the first parent of u and then finding the fourth parent of that. And the 11th parent is basically finding the first parent of u, finding the second parent of that, and then finding the 8th parent of that. And we can remember that we're given all of these parents because we've pre-computed them. So each of these parent jumps takes O of 1. And like here's an example. The fourth parent of 7 is 4, and the parent of 3 is, sorry, the fourth parent of 7 is 3, and the parent of 3 is 2. So the fifth parent of 7 is 2. So I guess like another example here is, let's say we want to find the 13th parent of u. We see that 13 decomposes into 2 to the 3 plus 2 to the 2 plus 2 to the 0, which is basically 8, 4, and 1. So we'll start off by finding the 8th parent of u, which is u, which is 16 in this case, and the 8th parent of u is 8. Now we'll look for the 4th parent of 8, which is 4, and we'll look for the first parent of 4, which is 3. And you can check that 3 is the 13th parent of 16. And each of these jumps takes O of 1 because we've already pre-computed these parent arrays. And since each node each number has a binary representation that takes like log of that number, and our numbers only go up to n, we'll have O of log n jumps per query. Like you can see here that our depth, the depth of 16 was like 16, but it only took 3 jumps to get to 3. So this is like kind of how we will do our kth parent queries really fast.
Yeah. So I guess first, are there any questions on either how to construct them or how to perform queries? Yeah.
Does this mean you have to store log n parents per node?
Yeah.
Yeah. So yeah, it's like O of n log n memory.
Any other questions? Okay, we'll get just right into implementing this now. So the problem we'll be using is basically the problem we just saw, where we're given like n nodes, in this case employees, and we want to find their kth parent, in this case like the k bosses up the hierarchy. And we want to do this fast since, again, n and q are big, so we want efficient queries. So how we can do this in Python is, so I've created some, I guess, like sample stuff to load in our data. What we're given is the bosses for each employee. So for employees 2 through n, we're given what their boss is. So this basically gets the bosses for employees 2 through n. And then what we want to do next is we want to begin constructing our binary lifting like pre-computed array, since we want to be able to handle queries efficiently. So we'll call that array par, and this will be a like par of I u means 2 to the I parent of u. Wait, is someone highlighting the code? Okay, whatever. Oh, okay. Yeah, so we'll first initialize this as just kind of like an empty array with nuns everywhere. So we'll do like none times, oh, and first we need to figure out, since we, the I here represents the 2 to the ith parent, we want to figure out like how many i's do we want? Like what's the biggest 2 to the I that we need? So in this case, n can be up to 2 times 10 to the 5. So as kind of a loose upper bound, we only need to be able to jump up 2 times 10 to the 5. So we can set the log 2 of that is about 18. So we'll set that to be 18. So we only need I up to 18 in this case. We'll have a thing for every single node. So so this kind of constructs like an empty none array for everything we need to pre-compute. Then notice that par 0u is just direct ancestor loss. So we can just kind of copy our line into par 0u. Okay, ignore this. So what this does is it sets the direct ancestors to be this array. And this array sets the parent of the root, like the node 0, to be none, since it has no parent. And it sets the parent of everything else to be the parent that was given in the input. So this constructs par 0. Then we want to construct our remaining like par 1 all the way to par like 17. So we'll iterate through everything up until log 2. And we will also iterate through because we want to calculate this for every single node. So for u and range n. So this calculates it for every single node. So to calculate 2 to the ith parent of u, we need par 2 to the I minus 1 parent of the 2 to the I minus 1 parent of u. Since if we compose it twice, we'll just get the 2 to the ith parent. So we'll try like P1 is the 2 to the I minus 1 parent of u. So right now, if this is none, this means that we've already hit the top, like there is no 2 to the I minus 1 parent of u, which means there is no 2 to the I parent of u either. So we'll set this. Otherwise, there is a 2 to the I minus 1 parent of u, so we'll calculate the 2 to the I minus 1 parent of that as well. So this gets kind of like the second jump of 2 to the I minus 1, and we'll just set the 2 to the I parent to this. Are there any questions on kind of this construction approach? Okay. So now that we have kind of all of our 2 to the I parents built out by kind of composing them one by one, we can create like a lift function, which takes in a node u and computes the kth ancestor. So what we want to do is kind of use a binary approach, where we kind of look at all of our, like the bits in our k, and make 2 to the I jumps based on those bits. So how we'll do this is we'll start by iterating backwards from the most significant bit down to the least significant bit. So we'll start So what this does, it iterates backwards, and then we'll check if k is greater than or equal to 2 to this power. That means that it has this bit set because it's greater than it, so it'll have a 1 there. We'll kind of remove this bit from it by subtracting it off. And then we will take u with a 2 to the I jump. So u is, so what this does is basically at every single bit that is set, it will jump up by 2 to the I. And after we look at all the bits of k, that means we'll have jumped up exactly k times, since we'll have read through the entire k's binary representation. And then we can return u. So are there any questions on, I guess, like either how we look at bits here or how this lift function works? Okay, so now that we've created our lift function, we're ready to answer queries. So we're given q queries. And they're given in the form x and k. So x, k. And in this case, x is 1 index, so we'll make it 0 index. And we want to be able to, we just want to find the kth ancestor. So we can just say kth ancestor equals lift of x by k. So this is just kind of calling our lift function to do this in log n time. So after we have our ancestor, there's, oh wait, I actually forgot one case here. So if, so after we lift up u by this much, it could be none because it's like, it doesn't have a 2 to the I ancestor. And we want to like, let's say u has depth like 2, but we want to lift it up by 10. That's not possible since it will like go past the root. So if u is ever none, we'll just return none, since that means like there is no kth ancestor of u. So now that we have the kth ancestor or none if there's not, our problem also wants to check like if such a boss doesn't exist, we want to print -1. So if kth ancestor is none, we print -1. Otherwise, we print the kth ancestor +1 because we want to convert it back into a 1 index. So let's try testing this code out now. Let's click run code, and we get 3, 1, -1, which means that after we lift node 4 up by 1, we'll get to node 3, since 3 is the ancestor of 4. Yeah, and then if we lift 4 up by 2, we'll get to 1, since 1 is the second, like the parent of the parent of 4. But 4 has depth 2, so if we lift it up by 3, we get -1 because it has no third ancestor. So this code works on the samples, and we can try testing it out on the actual judge. One thing to note is that this doesn't use depth first search, so we don't need the sys.set recursion limit for it to pass. So let's try submitting this. Should run. Yeah, okay, so it got accepted in about like half of our allotted time. And if we used our naive approach of just going up 1 by 1, we definitely would have done it exceeded. So binary lifting definitely helped a lot in this case. So do you have any questions, I guess, about any of this code? Also, this code will be available on the slides, which are posted, so you'll be able to access them. And any questions? Okay. Let's go on to our last topic for today, which is lowest common ancestor. So this will kind of build up upon both the DFS that we learned earlier, and it will use binary jumping that we just covered. So what is the lowest common ancestor? It's basically the lowest node that's an ancestor of the 2 nodes that you want. So for example, the lowest common ancestor of nodes 9 and 10 in the tree on the left is node 2, since that's the lowest node that's like a direct ancestor of both 9 and 10. Similarly, for nodes 3 and 4, their lowest common ancestor is node 1, since that's basically the only node that's an ancestor of both of them. And one application that you could use LCA for is to find the distance between two nodes. For example, let's say you wanted to find the distance from 9 to 10. That would mean this path right here, and the answer is 4. But there's not really an obvious way to do that without first computing the least common ancestor, since it kind of like goes up to the least common ancestor and then goes back down. So if you can find the least common ancestor, you can find the distance by just checking the distance in depth from these two. That's the distance from 9 to the least common ancestor, and then checking the distance in depth from these two, which is the distance from 10 to the least common ancestor, and then adding them together, giving you your total distance. So that's just kind of like one thing LCA can be used for. Next, we'll focus on how to build LCA, perform LCA on two nodes that have the same depth. This is like a slightly simpler version of our full LCA algorithm. So we'll start with finding the LCA of nodes 7 and 11. So these are of the same depth since they're the same distance from the root. And we'll just kind of go up one by one to their ancestors until they're equal, since the LCA is the lowest node that is an ancestor of both of them. So if we go up one ancestor to 6 and 10, they're still not equal. So let's try going up another one. 5 and 9 are still not equal. And if we go up another step, 4 and 8 are still not equal. But then if we go up 4 ancestors for both of them, we get that they're the 4th ancestors of both of them are equal. So, and also if we keep going up, they're going to still be equal. So we can conclude that our LCA of 7 and 11 will be node 3, because that's the lowest node that it begins to, like their ancestors become equal. Are there any questions, I guess, about the definition of LCA or how we came up with the LCA using kind of this? Okay. So we can, from this, we can arrive kind of at a slow LCA algorithm where we just iterate up through the parents each time until we arrive at something that's the same. So you can see that code right there. However, that code is O of n in that it will take, since you're just going up one parent each time, it can be pretty slow. So one thing you might notice is that, hey, we're taking like a lot of parents. And the algorithm we just covered, binary jumping, made it pretty easy to take a lot of parents really fast. So we can try applying that. But in order to do that, let's first transform this problem of finding the minimum k so that the parents are equal, which is what the LCA is, into finding the maximum k minus 1 so that they're not equal. Since if you look at the LCA, if you go up one less than that, they're not going to be equal. So for example, the LCA is 3, but if you go to k minus 1, it'll be 4 and 10. So you want to find the maximum k minus 1 so they're not equal. Does that reformulation, does anyone have any questions about that new formulation of this problem? Okay, so we can find k minus 1 like a single bit at a time using binary lifting. So we don't know anything about k minus 1 right now, and we want to find the LCA of 9 and 15. So we look at the most significant bit first, and we can say, is this bit a 1 or a 0? We can try first setting it as a 1. So this bit represents 8. So we'll check, like, is the 8th parent of u and v equal? So we look at that, 1 and 1, so it's equal. So the 8th parent of u and v are both equal. That means we jumped a bit too far to find k minus 1, since we want the parent, like the k minus first parent of them to be not equal. So we've jumped a little bit too far, so we'll set this bit to be equal to 0. Now that we figure out this bit is 0, we can continue with our next bit. So this bit represents 4, and we can check if the 4th parents are equal. In this case, they're not. So that means we've made good progress. We'll make good progress by taking this jump. And so they're not equal. We want to find the maximum k minus 1 such that they're not equal, and this jump gives us progress. So we will set this as a 1 to like take it up with. Now, given that we have 0 and 1 as our first 2 bits, we want to check if this bit, which represents 2, is a 0 or a 1. So we'll try going up another 2 and see if they're equal. So we'll take the second parent of what we already have to check if they're equal. And yes, they are equal, so we've jumped a bit too far again. So we'll set this to 0. And finally, to check this last bit, we'll go up one more parent and check if they're equal. So they're not. That means we've made good progress. And we know this bit is a 1. So after we've gone through every bit and set them all to 0 or 1, we're guaranteed to have found the maximum k minus 1, such that it satisfies the property that the k minus first parent is not equal. So now that we've found k minus 1 using this kind of one bit at a time approach, we can easily find k by just adding 1. So k equals 6 here. We found that k minus 1 is 0, 1, 0, 1 in binary, which is 5. So our LCA is the 6th parent of these nodes, which is 3. I guess any questions about this one bit at a time approach? Okay, so I guess as another quick simulation, what we can do is kind of go through a for loop and iterate down from the biggest bit down to the smallest bit and check if you take this jump, will it be the same or not? So in this case, we check, like, is the 4th parent the same? And the answer is no, so we'll take that and set u and v to be their 4th parent. Then we go through the loop again and we check the 2nd parent. And they are equal, so we've gone a bit too far, so we don't take this one. And finally, we check the first parent of them, and they're not equal, so we'll take this. So after this, we found k minus 1, and finally, to find the LCA, we just take the parent of the k minus first ancestor of either node. I'll be implementing this really quickly soon, so don't worry if this code is a little confusing. I'll be explaining it in a bit more detail. And how we can arrive from this same depth LCA algorithm to our full LCA algorithm is pretty simple, actually. So we just need to make, for any 2 nodes, we want to make them the same depth. So without loss of generality, we can assume that the depth of u is more than depth of v. So like u is down here, v is up here. If this were not true, we can just swap them. Then we want to bring u up to v's level. So u is depth u minus depth v away from v's level. So if we bring u up by that much, they'll now be at the same depth. And we can just run the same depth LCA algorithm on that and find the LCA of any 2 arbitrary nodes u and v. And this algorithm takes O of log n time per query, since for each query, it's just you iterate through like the bits 1 by 1. And the pre-computation time is n log n because you need to build your binary lifting array. And now I'll quickly do a live coding in like 5 minutes. So this problem is just given a tree in the same format as last time. We want to be able to answer a bunch of queries about what the LCA of 2 nodes is. So I'll open up this. I'll copy over our binary lifting thing from last time. I'll slightly change how we do input, since here we're given 0 indexed. We're given 0 indexed parents. So I'll remove this. Also, here, n is 5 times 10 to the 5, which is slightly bigger, so I'll increase our log up to 19. This will construct, this will still construct our parent array the same way, since we need binary lifting. We'll keep this here as well. But then, now we need to run our LCA algorithm. So to do this, we first need to figure out the depth of all of our nodes. And if you recall from the beginning of our lecture, we can do that with DFS. So we'll first construct an adjacency list, where we'll have adjacency is, and then we'll iterate through, so for I in range n, or for v in range n, the parent of v is, we can just use like our 2 to the 0th parent of v to find its parent. And then we can set the adjacency list of the parent of v. Or I guess in this case, it's kind of like the child of the parent of v to v. Then we can run DFS, in which we iterate through our node, and we iterate through our node, and we call DFS on the child. Notice in our adjacency list we don't store, like, we don't say that a node is adjacent to its parent, since we only have kind of edges pointing downwards. So our DFS can be a lot shorter. We'll also calculate all of our depths. So we'll initialize them all to 0, and we'll set the depth of the child to equal depth of v plus 1. So after we run this DFS with DFS of 0, we'll have all of our depths stored. So now we can create our LCA algorithm, which takes in 2 nodes u and v. So we first want, like, without loss of generality, we have u is like deeper than v. So if depth depth u is less than depth v, we'll swap them. So u v equals v. So now we want to raise u up to v's level. So we'll say u is the lift of u by depth u minus depth v. So after this, u depth u equals depth. So now that we have them at the same level, we can run our same depth LCA algorithm. So iterate from, we'll iterate backwards, and every time we'll check if we take like 2 to the I jump up, will the nodes be the same? If they are the same, we've jumped too far, but if we haven't, we'll take that jump and we'll keep repeating. So if the 2 to the I jump of u is not equal to the 2 to the I jump of v, that means we want to kind of take these jumps. And after this, we'll have found kind of like k minus 1. So like the nodes right below the LCA. So we can just return the direct parent of either u or v, since that will be the LCA. Next, we can perform our queries. So we're given nodes u and v, and we simply want to output the LCA of them. So this code should just perform our LCA function and output it. So we can now test our code. So the reason this happened is because the parent of the root was none, and we don't want to set that, so we'll just start from the node 1 instead of node 0. So if we run this instead, wait, what?
If u equals v, then we should just.
Oh yes. So here I missed a case. If u is v, then we don't have to perform this algorithm. We'll just since if u is v, then we don't want to like go up again. So if u is v, we'll just return u. Since if they're the same, then like it is the LCA. So if we then run this again, okay, we get 00022, which is the answer that they also have. So we can try submitting this now. And this will take a while to judge. Oh wait, one thing before we submit it, since this requires DFS and the inputs are really big, 5 times 10 to the 5, we need to do just that set recursion limit to like something really big, like 1 mil. This should still work, and now we'll submit this. So if we didn't submit this, this would like runtime error, since it would like run into our recursion limit and then start erroring out. But with this ish, what? Why is this an illegal language? Huh? Okay, I don't know if this will time out, but wait. Sorry, give me a sec. Okay.
Huh.
Okay,
Wait,
well,
what type of people right now?
I've submitted this code previously, and we can see that it passes. With set recursion limit 1000. I guess we have some problems on this in our problem set, so let me know if it's also bugging on your end. But yeah, this code works, I think. So I guess, do we have any questions about this in the meantime? Especially in like how we calculate LCA, like why we need this if statement. Okay, well then, that's the end of our lecture today. Please scan our attendance form for a raffle ticket and also leave feedback.